In my lab 2, I observed the motion of a falling paper ball, and my objective is to understand and predict the motion of this ball. And I can use Newton's second law to model the ball's movement, and I found that my predictions are very accurate to my experimental results. So here's a video of my falling paper ball. So in order to model the ball's movement, I have to start off with a fundamental principle, Newton's second law, which states that the final velocity equals the initial velocity plus the net force acting on the object divided by the object mass times the change in time. So the main mystery component here is this F net force. And since the ball is just moving down, the only force acting on the object that we're first going to dive into is the weight force. So the weight force equals negative mass times gravity times j hat, which gives direction to the vector in the y direction. And after plugging this in for our net force in the module, as you can see when you run module, the ball's movement is very similar here, and this graph is a parabola. The ball drops just like that, and it looks very similar to this graph right here. So now we want to compare our experimental and model prediction results. So here is the plot of the model position without any drag force with the experiment position, and it is very, very accurate. Now there is another force that we can look at that could contribute. If this is very inaccurate, it could contribute to y, and this is what we call the drag force. And so for the second model prediction line I also incorporated a drag force. And what a drag force is in this case is just technically the air resistance shown in the object. And the drag force always moves in the opposite of the object's direction and increases as the velocity increases. So for the second model prediction line I stated that my F net force equals the weight force plus the drag force. And this drag force equals negative b, which is the constant, times the magnitude of the velocity squared times the unit vector of the velocity. And now here is a graph of both of the lines with the drag force and without the drag force. And as you can see, they are very close together. But this drag force, when you add the drag force, it makes the line slightly smoother and a little slower because the drag force is acting in the opposite direction of where the object is moving, so it slows the object down. So now we can discuss which of these models predicts a terminal velocity. And it's hard to tell with such a short time span here, but this blue line eventually evens out into a solid, straight, steady velocity, which is the terminal velocity, where the drag force equals the weight force. So I'm going to pull up another chart which is through about 3 seconds of time, and as you can see, it's this blue line here. It, with the drag force, it eventually evens out to a solid line. Another question that comes up is that if the object was initially thrown downward, would the terminal velocity be the same as the case where the same object was initially dropped at rest? And this graph here shows that the terminal velocity would be the same either way, because as you can see here, this object initially released at a very quick 20 meters per second rate actually slows down to the terminal velocity state that is even with this slope here on this above line, where this blue line is going from rest into terminal velocity, speeding up. And you can see that both of the terminal velocities are the same, and the initial conditions do not matter. And And those are my observations from Lab 2. Thank you for your time.